Okay, so we're learning about string reassembly using the human genome. An analogy to the human genome stored on the DNA is that of a bunch of instructions stored in a book. So there's 23 chapters or chromosomes. Each one contains 48 to 250 million letters without spaces, and then hence the book contains over 3.2 billion letters in total. It fits in the cell nucleus size of a pinpoint, and at least one copy of the book is contained in most cells of our body. I think we talk about now the Human Genome Project. Oh, yes. We care about the 48 to 250 million letters without spaces that are contained within the DNA. There was this huge project in like the 2000s to map the entirety of the human genome, and they thought it was going to take like 20 years because humans are so complex. But I think we found out that we don't have that much more DNA than that of like a chicken, or I think we're like 90% similar to bananas. There's some fun fact where humans are not that special in terms of DNA. Oh, right here. It was designed to determine the entire sequence of human DNA, all 3.2 billion characters. And they did this through sequencing, which was done piece by piece, because it was pretty impossible to take a look at the entirety of the 3.2 billion nucleotides and try to map out all of them. Just impossible. So what they did is they sort of broke things up into chunks, which is a very common theme in computer science. A lot of the recursive methods that we use, the main deal with recursion is that you break things up into simpler parts and then you combine the answers because it's a lot easier to solve a bunch of simple problems than it is to look at an entire 3.2 billion length sequence. Okay, so what they did is they used enzymes like pizza cutters, and they chopped up the 3.2 billion strings of characters into a bunch of different fragments, each on the order of around 1,000. So a lot more fragments than that, but you get the idea. And then what they did is they used machines that could physically sequence each of them to determine their mathematical models. So instead of saying, well, what's the first character of the 3.2 billion? It's a lot easier to say, well, what's the first character of this 1,000 length genome? And they did that over and over and over again for all however many sequences that they got. And so then what they had was they had basically like sequence one looked a little something like this. A, C, D, C. Sequence two looked like this. G, C, T, A, G, something like that. And they had that for like millions and millions and millions of sequences. Then what they did is what's actually relevant for our project is they had to figure out some way to combine it back together in order to get the full picture of the 3.2 billion. An important thing to note is that some of these sequences were overlapped. So they weren't able to cut them perfectly, but they were able to get it pretty close. So for example, sequence one, sequence two could be something like this, where sequence one actually also contains the beginning of sequence two. So you have a bunch of string fragments, and your goal is to reassemble them. String reassembly by fragments. Next, they use computer algorithms to reassemble the original very long string model from the model of its fragments by combining the fragments based on their overlaps. So if you have thousands or even millions of these sequences, let's say there's like 2 million. This is not an easy task. But what's one way to do it is, or what's known as the naive approach, is to pick the two fragments with the most overlap and combine them into a longer fragment. So let's say every single sequence had only one overlap, and these two were the only two that had 2 characters of overlap between them. Well, what you do is you take these, you combine them, and now one becomes G, C, T, A, C, T, G, G, C. Now we've combined these 2 fragments of strings based on their overlapping characters into one string. And you repeat this over. Question or
question? So, like in that case, the suffix of one is the same, or the prefix of one is the same as the suffix.
Yes.
How would you know which
That's a good question. This is a poor example because this wouldn't occur. Oh, well, actually, we'll get to that. We'll get to that. Hold on. You're like, I'm going to say 6 slides ahead. So pick with the 2 overlap and combine them into a longer fragment. You repeat this over and over again until you have, well, here's an example. Example pair of strings, same thing. CG is the overlap, and so you combine them into a single string. Prefix of one is the suffix of the other. The idea is that both of these shorter strings could have been fragments of this longer string. So when you're cutting up the fragment, maybe you accidentally cut a little far on one end, a little short on the other end. And then if you repeat this over and over again, you might be able to combine them. The math model of soup is a finite set of strings of characters. So it could be a set, which we talked about on Tuesday. So here's the first case, is that you continue the process until there is only one fragment in the soup, in which case you can declare that you have reassembled the entirety of the human genome correctly. However, let's say that it was right, and instead of being this way around, it should have been the other way around. So it should have been A, C, T, G, G, C, E, A, C. And because of that, that kind of populates or goes down the line, and you have a bunch of fragments that no longer can have the correct reassembly because you messed up earlier in the process. Well, then you end up with a bunch of fragments that cannot be combined, which is bad. So what you do in that case is you start over and try again. It won't be a problem for your lab, I don't think, or we'll show how it cannot be a problem. Does that make sense?
Yeah.
Okay. Even if there is only one fragment left, it might not be the original long string that was chopped up, but it is a good guess. Since we're only working with 4 characters, or they were only working with 4 characters, there was a potential that there was parts of the human genome that were not technically supposed to be overlapping, but were overlapping. And this is why the naive approach is not the most efficient way to do it. So, how this comes about in our project is you're going to do the same thing, although we are not going to make you reassemble the entirety of the 32 billion human genome sequences, but you're going to be using the Gettysburg Address, a famous speech by Abraham Lincoln, a lot shorter. But what will happen is you will get a bunch of fragments of the speech. I'm pretty sure the Gettysburg Address is like 4 score sentences, right?
Let's say, yeah.
Thank you. 4 score, or maybe it'll be like 4 sco. And then you'll have another one which is like R score. That's a lowercase. And set. Maybe you'll have one that's like 7. Something like this. You'll get a bunch of strings that are like this, and your job is to, using the same process we talked about here, combine these together until you get the entirety of the address. 4 score and 7 years ago, so on and so forth, until you get the entirety of the speech. And there is a bunch of methods, and it describes to you very clearly how you do this in the project. So if it seems very complicated, do not worry. But the way that we're going to be using, or the way that you're going to do this is using a sequence, which is the next data structure that we are going to talk about. But before we go forward, does this process of taking overlapping strings where one is the prefix of the suffix of another and combining them, and then doing that process over and over again until you get a main string, which is the original text that was split up, does that make sense? Okay.
I have a question, this might not apply, but what if it's like, what if it, like, say you have like 4 score SEO and the next one is like COR, if there's overlap, are you supposed to?
Like this?
Yeah, so like, would that be like, since the first 2 spots of that are already on the 4 SCO, or would you just snip it, or?
Yeah, so what you would do is a bunch of ways you could do it. You could say like, hey, give me everything but what gets overlapped here, and then just append this on the way.
Okay.
Or you could do the opposite. You could say, hey, give me everything but the suffix here, and then just.
That makes sense.
So you're gonna work a lot with strings, which is fun. The string indexes. Interesting. Okay, questions on this before I erase it? Awesome. Okay, the next data structure that we're going to be talking about is the sequence. We talked about the set on Tuesday. We talked about the queue before that. If you remember, the set was based off of the set Java data structure was based off the mathematical set in math, which was a string of keys or a set of keys. We also talked about the queue, which mathematical counterpart was a string of t, where t is just a generic type. Today we're going to be talking about the sequence. And what you'll notice is that the sequence is also mathematically modeled by a string of t. So if you looked at the mathematical models of a sequence and a queue, you would not be able to tell the difference. In Java, however, there is a main difference between the queue and the sequence, mostly the methods you use to manipulate the mathematical model. So technically as well, you would not be able to tell the difference between, well, you would be able to tell the difference between a set and a string of t because the set would not have duplicates. But if I gave you, say, something like this, was a mathematical model, I said, hey, here's a mathematical model of a Java data structure. Is this a queue or a sequence? You would not be able to tell me the difference because they're both modeled by a string of keys. You would be able to tell me that it's not a set because it contains duplicates. But in the back end, or mathematically modeled by the queue and the sequence is the same thing, which is a string of that generic key. I'll leave it for a second. Okay. Sequence. Sequence component allows you to manipulate strings of entries of any arbitrary type T through direct access by position similar to an array. It's another generic type like queue and set, and it's one of the alternatives to an array. So if you remember, one of the cool things about an array was if you knew exactly where your element was, you had an array called A. A little bit something like this, where 0, 1, 2, storing natural numbers, say, just for this case, and you knew that your value was stored in the second index location, you could call A sub 2, and that would give you at least the reference location to the element that you wanted to reference. Sequences are just like this. You can, if you have the index location of the element that you want to look at in a sequence, you can index it. Not the same with queues. Where is the only place that you can remove elements from a queue? Yeah. From the front, exactly. So if this was, say, a queue, you would only be able to remove the 0th element. Now you could like reverse it and then remove the back one and then reverse it again, but that's besides the point. Just like a grocery line, it would be very annoying if that second person all of a sudden just got to the front of the grocery line because you can't cut. That's like illegal in both Java and in real life. Okay. So alternate best practice to an array. Sequence is an OSU COC component, which means we are going to see the diagram trademarked by Bucci, I believe, and patent pending. Extends the standard interface, has a kernel, has an actual interface, and then is implemented by 3 separate class types. Again, when I told you that you would be seeing this in your nightmares, I was not lying. Standard has 3 methods. Who can tell me 1, 2, or perhaps even 3 of them? Yeah. Clear, new instance, and transfer func. Clear sets it back to an initial value. New instance creates a new sequence object based on the dynamic type that you call it on. So we have, say, S1 equals new sequence 1L. And then we have S2 equals new sequence 2. And what's the third one? Oh, it's 2L. Interesting. And then we have S3 equals new sequence 3. S1.new instance would return a dynamic type sequence 1L. S2 would return a dynamic type sequence 2L. And S3 would return S3.new instance would return a sequence 3 dynamic type. This is important if you're writing a method that takes in a sequence because you cannot be sure which of the 3 sequences the user that is passing, or the client in this case, is passing into your method. So if you have a method that takes in, say, just a generic sequence type, sequence S4, and this is some foo method. As the implementer, you have no idea what type the user is going to pass in. They could pass in a sequence 1L, they could pass in a sequence 2L, they could pass in a sequence 3. You don't know. So best practice, if you need to make a, say, fifth sequence for some whatever reason, is to say sequence S5 equals S4 dot new instance. And in this case, if the user passes in a sequence 1L, you have a sequence 1L. If they pass in a sequence 2L, you have a sequence 2L. And if they pass in a sequence 3, you have a sequence 3. It's a very cool and powerful method. And then transfers all of the elements from one sequence to another, and then resets that other sequence back to the initial value. Questions on standard interface? It's pretty standard, you could say. Sequence kernel has 3 methods: add, remove, and length. And then in that final sequence 1, we have 6 other methods: entry, replace entry, append, flip, insert, and extract. And we'll be going over all 9 of them today. So the value of a sequence variable, like we talked about, is modeled as a string of entries of type T. So type sequence is modeled by a string of T. So when we're talking about entries within the string, we could have something 1, 2. That could be the mathematical model of a sequence. Only has one constructor, I believe, which is the no argument constructor, which gives you an empty sequence. Sequence is a reference type. Like all other reference types or reference type data structures that we talk about, can only store reference type variables. So if you want to store integers, chars, doubles, booleans, you have to use the big versions that are provided by Java. So when we say sequence of type integer si equals new sequence 1L, we're doing a lot of things. Saying, hey, you want to make an object that implements the sequence interface, which is here. So it should have 12 methods. The 3 from standard, the 3 from kernel, and then the 6 from the actual sequence class. We're saying it should store integers of reference types, big integers, if you will. And we're saying it should be of implementation or dynamic type sequence 1L. So you should use, for any of the methods that I'm about to call on the sequence, the 1L implementation of those methods. Not the 2L, not the 3, the 1L. And that will make you an empty sequence. All right. Add adds X at position POS of this. It creates an alias to that reference. It updates this. Requires that you are within the bounds of the sequence. We index by 0, like arrays do. And it ensures that the element that you're adding gets placed at the location at which you are adding it. And we'll talk about what that means now. So, picture time. I was very happy with all of the pictures on the exam. I'll people do pictures. Okay. SI is a sequence, points towards a reference type data structure. Rectangle. And we have 49, the big integer, and we have 3, which is another big integer. Then we have Z, which is a big integer reference type, so it's drawn like this, and it has the value of 7. So when we call si.add, we pass it first a position variable at which we want to add it, and then we pass the actual reference that we want to add. It's important to note that the index location that you pass through, a good way to think about it is that is the index location at which the element will be inserted at. So you're not saying insert it after the first index, because then it would be second index. In this case, this is 0, this is 1. What you're basically saying is that after this call has been made, Z should be the first index. So what you're going to do is insert it here, and this will be a reference to that object type. Reset the bounds. 0, 1, 2. Z is now a alias to the first element in the sequence. That is going to cause problems if you are storing what? It's going to cause dangerous aliasing if you are storing either what? It's either mutable or immutable. It's a coin flip. That makes it easier. A mutable type. Sorry, I thought you said A mutable, immutable. Okay, a mutable type, and why? Exactly. So if you're storing mutable types, then you could eventually get to an instance where you call, say, z++, where my directive or my goal with this was to increase the value of the z variable. But since we have a dangerous alias here, I have now also indirectly increased the integer stored at the first location of the sequence, which is not something that I maybe wanted to do. So any mutable types, beware when you're using references. It's called dangerous alias. So afterwards, the mathematical model of our sequence is 0, 1, 2. We have 49, 73, and z is aliased to that 70 variable. Note the alias here, which you cannot see in the tracing table, but is important and dangerous. Okay, removes and returns the entry at position POS of this, updates this, requires that you're actually within the index. So you cannot call remove on index location 3 because we start indexing at 0. Other programming languages will index at 1. They are bad programming languages. You should not use them. And by that, I mean MATLAB. Okay, so if we have this here, where now 1 has been given anti-aliasing powers and is just a number of the sequence, z has moved on from 7 and is now storing -584. What we do here is we say that we want z to be equal to the object value that we are removing from the sequence at position 1. Oh no, why'd they swap it? Okay, so instead of being 49, 3, and 70, it's 49. Instead of being 49, 70, and 3, 49, 3, 7. So we're saying, hey, we want the object value at location 1. So object location 1 gets deleted. And we point z now to this object value that was removed. So z is equal to 3, the object value that we removed, and the sequence no longer contains 3. And then length reports the length of this. So, oh wait. Okay, so let's say that we have this sequence si, which contains 2 elements, and then we call si.length. What will be returned? 2. Thank you. I heard it. If the sequence had 3 elements, it would return 3. That's how length works. Okay, those are the kernel methods. Any questions on those? Be careful of aliasing. Length returns the length. Remove returns an object value. Okay. Entry is a way to report the entry at the position of this. This is essentially the reference type way of getting an array location. So a sub 0 is the alternative to this in the sequence, or I guess I don't know what the word is. The same thing in a sequence would just be called a dot entry of 0. Important thing to note is that it aliases the reference that you're pointing to at the entry. So 3, you're back in. Z points again to -584. Here you are 1, you are 2. So only call entry, we're saying, hey, give me the first entry of the sequence and give it to me as an alias to z. So z says goodbye, -584. Friendship over. 3 is my friend now. And you are alias to 3. Again, mutable types, dangerous if you have a mutable type, because now you have an alias to that 3. Note the alias here, which you cannot see in the tracing table, but you can see in the lovely drawing. Draw pictures, always draw pictures. Okay, replace entry replaces the entry at position POS of this with X and returns the old entry at that position. This one, if you're not going to draw any pictures for anything else, draw pictures for this one because the aliases and the references get confusing. So as an example, we have 4 reference variables that we need to keep track of now. 3, you're back out of the sequence. 5, you are 1. 49 and 70, that is correct. We have z, which points to -8. And then we have w, with reference location to negative 584. Okay. What happens here is we say that W should be equal to whatever entry we are replacing in the sequence at position 1. We're replacing that with Z. So position 1, first and foremost, you should do the insert first. So we're inserting or replacing index location 1 with Z, which means you become whatever Z is, which is -8. And then we were saying W should be equal to whatever was removed. So in this case, W now points towards 7. We've replaced 70 in the sequence with -8, and W now points towards that 70 location. So we have 49, and then we have -8. Z points towards -8, and then W points towards that old value of 70. First position in the sequence, Z, our alias, dangerous, bad. Don't do it if you have mutable types. Okay. Note the alias that was created here. Another example, if say you just wanted to swap the values, the way that you could do it. So 70 back in the sequence. And then we just have one variable, which is -8. W by saying first, put whatever the value that we're passing in. And then we're just swapping the reference values. So now Z is going to point towards whatever was removed. 70, -8 gets added to the sequence. You're swapping the reference locations, which is better because you do not create an alias. So 49 and -8, and then Z is stored in 70. Good on replace entry. Going once, going twice. Sold to another slide for some reason. Avoids the alias. Sold to append. Append concatenates or appends an entire other sequence to the end of this. So they don't even have an example for that. But if you had a sequence of, say, 1, 2, 3, I'm not going to draw the full picture. And then you have a sequence of 4, 5, 6, and you call this is S1, this is S2, and you call S1 dot append S2. Afterwards, this sequence will be 1, 2, 3, 4, 5, 6. If you called S2 dot append S1, it would be 4, 5, 6, 1, 2, 3. Order matters. It's not like sets where if you called S1 dot add S2, what you would be left with is 1, 2, 3, 4, 5, 6. Well, I guess it still would be 3, 4, 5, 6. Oh, what I mean is if you called S1 dot add S2, you would be left with 1, 2, 3, 4, 5, 6. If you called S2 dot add S1, you would be left with 4, 5, 6, 1, 2, 3, but they would be the same set because sets do not worry about order. Questions on append? Okay. Flip, reverse, or flips this. So if you called flip on 1, 2, 3, it would become 3, 2, 1. If you call flip on S2, it would become 6, 5, 4. Okay. Perhaps the last interesting one is insert, which inserts an entire sequence at position POS of this and clears S. Important to note that it clears S. So what you can do is you can say, hey, if I want to insert S2 into S1 at the first location, that means at the first location, the second sequence should start. So 1, 4, 5, 6, and then the rest of the elements that were in S1 before things were inserted get added after you insert S2. Oh, there's an example. More picture. So these are values too. So we have SI, which points to a 3 value. And 1, 2, it's pointing towards 862, 8, 6, and 92. And then we have another sequence, which we're calling SI2. This is SI1. Sequel points towards another reference location, which only has 2, which are 1 and -7. What we mean when we say that we want to insert SI2 at the second position of SI1 is that starting at position S2 should be all of the variables of S1. So, I'm gonna draw this in quite possibly the worst way possible, but what you could essentially do, if you wanted to draw a picture, is erase this, and then sequence becomes this. Yes. So now we have the world's most beautiful sequence with 8, 6, 1, -7, and 92. And SI2 gets cleared. So this gets pointed towards a new empty sequence. 8, 6, 1, -7, 92. And SI2 is blank. Does that make sense? People get messed up on index locations, so just make sure you're keeping track of those. Okay, this one's actually kind of a behemoth. Extract removes the substring of this starting at position POS1 and ending at position POS2 -1 and puts it in S. This is like the substring method with strings, except instead of characters, you're working with entries within a sequence. So you need to pass it three things: a position to start at, a position to end at -1, as well as a sequence to store everything in. So I don't know why they didn't keep the values for me. 92, 27, 2. 1 set. This is our SI1. SI2 now, for whatever reason, contains more values. 1, -7, 562. And then we get into our call, which is we're calling extract on S1, which is start at the first position, finish at the third position, and store it in SI2. So, like a substring, what we say is we want to extract starting at the first position, ending at the third position, which means we actually don't use the third position. It ends at the third position. So only the first and the second element should be extracted. And those should be stored in SI2. And this picture is going to be weird. Pretend that there is a portal here and a portal here. And SI2 now points towards this version. If you do this on exam, you will not lose points, by the way. And yes, I think that works. 2 sequences. With a portal in between. Beautiful. So now SI1 has first element 8, go through the portal, and then it has 27 and 0. And then the second one, which is shoved between the portal, is 6 and 92. Does that make sense? I can redraw it without the portals, but I think the portals are cool. Questions on extract? Anyone notice 1, -7, and 562 just got deleted by garbage collector? Goodbye. Oh, that's everything. Okay, questions on sequences? Yeah.
I didn't see earlier, but did append clear the sequence being appended?
I think so, yes. Clears S. Just keep that in mind. All right, exam time. I have them, they're in alphabetical order. Oh. So when I call your names, come up and grab it. Agna. Alyssa. Anya. Anurag. Arnav. Brandon. Brooklyn. Caden, I do Brandon. Brooklyn, Caden. Christian. Danny. Ethan. Farhan. Ibrahim. Isaac. Sorry. Gene. Jessica Sun. SEQ as well. Jintian. Logan. Mark. Maria. Max. Micah, Luca. Muktasi. Neil. Otis. Nay. Richard. Rohan. Sai. Siva. Stephen. Kamulin. Varsha and Varun. Youngwon. So. Anybody I did not call here. If you have questions, please Slack me or let me know. I can explain reasonings. The average was like a 79, which was like 9 points higher than my midterm 2 last semester, which is good. Not last night. I will give you points on it. It will probably be tomorrow night because I have to go.
Yeah,
study.
don't worry about it.
Yeah.
Do you want me to remind you?
Yes.
Okay.
Send me a message tomorrow night so that I can do it.
Okay. Good luck on your exams.
Thank you.